Example 4. A derivative of f of x equals root x for x greater than 0. Now, since we haven't talked about the actual derivative rules yet, we can only feel our way about in the dark by using the same old method of f prime of x is equal to limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so what is f of x plus h? And how can we manage to somehow make this not have a whole bunch of root signs that we can't put together? Well, let's see. Limit h goes to 0 of root of x plus h minus root x over h. Okay, wait a second. What's one way we can get rid of all these radicals? Well, we can perhaps multiply by root x plus h plus root x. And down here, we can multiply by the exact same thing. X plus h plus root x. Okay, what do we end up with? We end up with x plus h minus x. But first we have to end up with this limit. Okay, so x plus h minus x. And this is over h times root of x plus h plus root x. So, clearly, this cancels. And thus we have h on top and h on the bottom. And how does that work? So this cancels out to a 1. Okay, so this is going to be limit as h approaches 0 of 1 over root x plus h plus root x. And when h is set to 0, we have 1 over 2 root x. All right. So what do we, well, more or less need to remember? Just to be polite to our teachers? We need to remember either to put a statement, or at the very least, to put what you're actually equaling on the bottom line. Okay, now this is for x greater than 0. The thing is, this returns to you an imaginary number if you set x to be less than 0. So the restriction here, given that x also can't be equal to 0, well, we may or may not, depending on convention, need to state the restriction. But just to be safe, for x greater than 0. Fine, there. Good? Okay, now, suppose we need to find the tangent line to the curve y equals root x at x equals 4. Here, we're kind of going to assume that it means y equals positive root x, because that's the convention in North America usually. Now, if it said negative root x, then of course we'd find something rather different. So here, f prime of x equals 1 over 2 root x. So, prime of x equals 1 over 2 root x. One of the easiest checks you can make for slopes is, oh, is it positive over this range? Or is it negative over this range? We know that root x increases at a decreasing rate. So 1 over 2 root x, well, as x gets bigger, this is going to get smaller and smaller. Okay, that works. And it's always positive. Okay, good. Now, for f prime of 4, then that's equal to 1 over 2 root 4, which is equal to 1/4. Okay, so I'm going to point out that tangent slope is 1/4. Now, often, once you get more experienced with this stuff, you won't necessarily write this. You just go straight to f of x equals root x. Sometimes you might even skip this one. And you'd go to f of 4 equals root 4 equals 2. So I'm going to make a note for our learning purposes that line goes through, or tangent through, 4, 2. And we'd have y minus y1 equals m times x minus x1. So y1 is 2. And this is equal to m, slope is 1/4, x minus 4. So we end up with y equals 1/4 x minus 1 plus 2. So 1/4 x plus 1. Now the question says, find the tangent line to the curve y equals root x at x equals 4. So our statement is probably something like, oh, the desired tangent is y equals 1/4 x plus 1. So in other words, the statements generally just restate the question. But I'm sure by this point we are familiar with that. Okay. Here we have a function. We have a graph. We have certain points on it that have slopes that are marked out for us. And we need to plot these points. So here, okay, let's say that's 13 or 12.5 maybe. So we're going to plot this on this graph. We're going to plot the derivative of this. What can we say? Well, here at, according to the scale, presumably -3, we have a slope of 0. And we need to go all the way to 12.5. And we have 5 grids to work with. That means we are most likely going to be dealing with this being 15. This is 0, of course. And this is -15 on the x-axis. So please note that the grids they give you to work with are not necessarily the most suitable for any given type of problem. Here, well, we need to... Okay, so this here, oh, approximately 8. This is approximately 4x units. So that's a slope of 2. So 2 is the highest slope we'll have to accommodate here. And then the most negative is presumably marked at this point. So -4/3. So not much. So let's say that this here is +2 slope. And this is -2 slope. At x equals -3, our slope is 0. Given our scaling, that means we need to cross this point here. And then at 3, our slope is -1. Now, given our scaling, that means we need to have this plot of the derivative cross here. Now, given the shape of this curve, what can we say about the progression of the slopes? It's most likely to be pretty close to a straight line. Now, if this was parabolic over that section, it would be a straight line. And, okay, slope -4/3 at x equals 5. That means here, more or less. Okay, so wait a second. That's a slope of 1 grid over, 1 grid down. Okay, what about here? Given that -1/3 more than -1 is how much of 2 grids per 1 unit of slope? It's 2/3 of a grid. Okay, and 5. Given that the horizontal scale here is 1 grid is 3, how much is that? Also 2/3 of a grid. So this actually should be just a straight line. Okay, and then what? Well, the slope goes back to 0 by the time we get to 9. Okay, so 9 would be here. Now, this is 1/3 of a grid away from that edge. It is 2/3 of a grid down. And guess what the ratio here is? Oh, 2 grids down, 1 grid over. This also strongly implies that this is a straight line when we plot the derivative. Well, the derivative function, to be specific. So, what about the e value here? The point that's marked as e. Well, that has a slope of 2, and that's at about 12.5. So just a little bit past this, and we're all the way up to about here. So this, well, it looks like it's parabolic, so it's going to be another straight line up there. So it more or less looks like this. So as we can see, with a nice smooth curve, if we graph the derivatives, then we may very well come up with a plot that is quite jagged. And what happens if we need to take a second derivative, i.e. the derivative of the derivative? Well, we would have points at which we just have no value. This would look like a step function. So one constant value, another constant value, and another constant value. Of course, there are functions that don't end up looking like such. For example, x to the third. You are welcome to try the derivative formula we showed you earlier, and try it twice, or even try it 3 times, and you will find that you get continuity every time. Actually, you can try it 4 times if you like, but well, that comes out to a completely different story. Now, what happens when we look at closed intervals? So including the endpoints instead of open intervals. Well, on open intervals, we can say, oh, this has a slope here because no matter how close we get to an endpoint, we can always get closer. So we can get infinitely close, and then, well, a smaller infinitely closer. So, If it's differentiable on an open interval, it has a derivative at each point of the interval. Okay, on a closed interval, well, at the endpoints, we can't exactly look on the other side of the endpoint because it's a closed interval. It's firmly bound to that endpoint. Now, if it's differentiable on the interior, like say this line here, if this here is B and this is A, then, while the interior it's differentiable, say this is a straight line, it would be constant slope. And, okay, we get closer and closer to there, and we see that it is still this slope. So we find the right-hand derivative at A. Notice that instead of the minus A minus H, which would be on this side, we use A plus H, which would be barely on that side of A, minus F of A, divided by H. And this approaches 0 from the positive side for H. And for B, well, we approach from this side, and that's the left-hand derivative at B because it comes from the left. So what happens when we find the right-hand derivative at B? Well, we find that, oh, this is a positive value, that's a negative value. Well then, that tells us that the function does not have a derivative at that point because the left and right-hand derivatives are not equal. Although it does have left-hand and right-hand derivatives there. Okay. Now what happens if instead of this sharp turn, we had a however tiny smoothed turn? Then we would have left-hand derivative and right-hand derivative, and then they would be equal. So this would be differentiable at this point. It would have a derivative at that point. And it would have a derivative over the entire domain over which this is true, i.e. there's a left-hand derivative and a right-hand derivative and they are equal. As opposed to this sharp turn where there the function is not differentiable, even though it's differentiable on both closed intervals on either side. If we say define C here and use C for a closed interval there. Okay, let's continue. Now in this example, well, we need to show that y equals absolute value of x. What is y equals absolute value of x? Okay, f of x equals absolute value of x is f of x equals brace bracket, well, or like set bracket, but anyhow, this is equal to x at x is greater than or equal to 0. And it is equal to negative x at x is smaller than 0. So, if we were to find the limits of the derivative at f0, we would find lim h approaching 0 from negative direction of f of 0 plus h. Why plus h? Why isn't there a sign change? Well, if h is approaching from the negative side, well, it's negative. So add a negative number. That makes it more negative, or makes it negative in the first place in this case. So, minus f of 0, and this is all over h. So this is equal to limit of h approaches 0 from the negative direction of negative 0 minus h minus negative 0. As we can see, these cross out nicely, and all over h, so this cancels out to, well, this cancels out to negative 1, and this is 1. So, this is equal to negative 1. Okay, Now what about the right-hand derivative? Well, that's limit of h approaching 0 from the positive side, and that's f of 0 plus h minus f of 0 over h. And that gives us limit as h approaches 0 from the positive side of 0 plus h minus 0 over h. I think we can all see that this comes out to equal 1. Since left and right hand derivatives are unequal at x equals 0, y equals absolute value of x is not differentiable. At x equals 0. So there goes our statement. We say that, oh, okay, left hand and right hand derivatives are not equal. Therefore, there's no derivative at this value. There is a theorem about differentiability and continuity. If f has a derivative at x equals c, then f is continuous at x equals c. This does not apply vice versa. F can be continuous and not have a derivative, as we just showed with the absolute value function. Because, hey, that's continuous at x equals 0. Is there a derivative there? No. But if you have a derivative, so a tangent line that you can draw, then at that point, it must be continuous. Alright, so in summary, these following points are all interpretations for the limit of the difference quotient. So this could be the slope of the graph of f of x at x equals x0. Okay, this could also be the slope of the tangent line to that curve, because, well, the slope of the tangent at the point of tendency equals the slope of the curve. This could be the rate of change of f of x with respect to x at x0. So in other words, the slope, because change of f of x per change of x is rise over run. And the derivative f prime of x0, well, why isn't it, f prime of x at point x0? It's because we just substituted it right in to have less writing. Now the derivative of y equals f of x is a new function, y equals f prime of x. This represents the slope of the tangent. So in other words, if we were to plot all the slopes of the curve along a new graph with x-axis and slope of f of x as your y-axis, we end up with f prime of x. So we can also say that this is instantaneous rate of change at any point on the curve. The derivative function is defined by the first principle's definition, which is this thing, if the limit exists. Because sometimes, such as with the absolute value function we talked about, it doesn't. And thus, it can be non-differentiable at a point or several points. Different notations for the derivative may include the following: f prime of x, y prime, presuming that you wrote that y equals f of x. If you just say that, oh, the vertical axis is labeled as f of x, then you don't use this. You use f prime of x. It can be dy over dx. So when delta is your symbol for change, what do you think d goes for? Well, in this case, it's also change. So tiny change in y per tiny change in x. In other words, slope. Local slope. Or df of x over dx. Now, why isn't f of x up there in the numerator? Well, convention, pretty much. So if the derivative does not exist at a point on a curve, it is non-differentiable at that x value. This can occur where, say, the function is discontinuous. For example, oh hey guys, we have a big gap in the domain here. I wonder what the slope is in that big gap. There's no slope, of course. And what about infinite discontinuity? Well, what's the slope there? Undefined. Or, well, we can have an abrupt change, which is represented by a cusp or a corner on a graph. Okay, so that's basically the fundamentals of differentiation and thus derivatives. And there are lots of rules, as you can probably guess, because we mentioned a few, which will be covered next section. Also next chapter in most textbooks, because, well, textbook arrangements may vary, but when you go through all the sections with us, you'll have covered all the standard curricula stuff anyway. So, see you later.